Welcome to our new session. Today we are going to discussing about geometrical isomerism. Our topics are methods of determination of configuration of geometrical isomers and conformation. Methods of determination of configuration of geometrical isomers. There are no general methods for determining the configuration of geometrical isomers, and these methods are employed depending upon the nature of the compound. And it has been found that geometrical isomers shows different physical and chemical properties. According to these properties, they are explaining the determination of configuration of geometrical isomers. So by physical properties, we have melting point, solubility, dipole moment and boiling point. And chemical properties by cyclization method and by converting into compounds of non-configuration, finally from the type of optical isomer formed. So let's start. Physical properties, that is melting point. In the case of melting point, trans isomer has higher melting point comparing with cis isomer. This is due to fact that cis isomer having two similar atoms or groups on the same side of double bond. Therefore, the molecules are unsymmetrical, hence they do not show close packing in the crystal lattice. On the other hand, that is trans, they having similar groups on the opposite sides of double bond. Therefore, molecules are well packed in crystal lattice. As a result, intermolecular force of attraction of trans is stronger than cis isomer. You can see the example, that is fumaric acid and malic acid. Malic acid is cis and fumaric acid is trans. And melting point of malic acid is 130 degrees Celsius and fumaric acid, that is 302 degrees Celsius. Solubility. As we discussed above, the molecules of cis isomer are less closely packed compared with trans because they have weak intermolecular force of attraction in crystal lattice. Therefore, this is isomer having higher solubility than the trans. So, malic acid, that is 79.0 gram per 100 ml, fumaric acid 0.79 gram per 100 ml. Dipole moment. Here, the cis isomers have higher dipole moment compared with trans isomer, that is which having nearly 0 or nearly 0 dipole moment. And the higher dipole moment of cis isomer is due to the orientation of two dipoles of cis isomer. They are in same angle. In the case of trans, they are in opposite direction, so they cancels out. Examples is dibromomethine, and this cis is dipole moment is 1.35 and for trans it is 0. Boiling point. The boiling point of cis isomer is higher than that of corresponding trans isomers. This is mainly due to the polar nature of the cis isomer. They result in the stronger intramolecular attractions. And the examples is cis 1,2 dichloroethene and trans 1,2 dichloroethene, and boiling point is more for cis because of polar nature. Next is this method of configuration can also determined by X-ray diffraction patterns, and here a crystalline substance produces certain pattern on a photographic plate. They can be used to calculate certain positions of atoms in the molecule. And that's about the physical properties. Next is chemical properties. First method is cyclization method. That is, cyclization occurs very easily when two reactive groups are close together. Since this is isomers, the reacting groups are very near to each other, so they result in the formation of cyclic compound. But in trans isomer, the reactive groups are far apart, so they are unstable to form cyclic derivatives. Example is malic acid, that is cis compound. They are getting converted into cyclic compound, that is malic anhydride. And next method, by converting into the compounds of non-configuration. In some cases, geometrical isomers can be changed into compound of non-configuration. It is presumed that during such a change, there will be no change in the isomerism. So that is a trichlorocrotonic acid. When they are reacting with water, we are getting fumaric acid. Then when they are reacting with zinc and hydrochloric acid, we are getting crotonic acid. And final method, that is from the type of optical isomer formed. So both geometrical isomers on hydroxylation, they gives us optically active compounds. For example, that is tartaric acid. So malic acid, when they react with potassium permanganate, we are getting mesotartaric acid. And fumaric acid, when undergoing reaction with potassium permanganate, we are getting plus or minus forms of tartaric acid. And this is about the determination of configuration of geometrical isomers, that is chemical methods and physical methods. Next, conformation. Conformation means they are different spectacle arrangement of molecules. They can be generated by rotating the single bonds. There is different conformations of the same molecule. We can call it as conformers or rotamers or conformation isomers. So these are the certain conformations, representation. There is wedge and dash, Sohos, Newman projection, etc. First one, the conformation of ethine. So ethine having two type of conformation, that is staggered and eclipsed. So in staggered conformation, the tetrahedrally attached hydrogen atoms of the carbon atoms are far as possible. Hence, the force of repulsion between them is minimum. Therefore, the staggered conformation of ethine is stable. Then eclipsed. In this conformation, tetrahedrally attached hydrogen atoms are very minimum distance with each other. So the repulsion between them will be maximum. Therefore, the eclipsed conformation is less stable. You can see that in figure. This is staggered and this is eclipsed. See, staggered, you can see that hydrogens are far as possible, and in eclipse that they only passes only minimum distance from each other. So the repulsion will be maximum in this eclipsed compared with staggered. So staggered is more stable than eclipsed. Representation of conformation. So there are three types of conformation, that is Sohos representation, flying wedge representation, or Newman representation. First one is flying wedge representation. We can also call it as clotted line wedge representation, and they are connecting with two carbon atoms. That is, you can see that is two carbon atoms. They are drawn horizontally in the paper. They can be drawn horizontally or any other way in paper, and the bonds above the paper, they can be in wedge form. That is, they are in wedge form, and dotted lines denotes the bonds that below the paper. Next, solid line denotes that is lying in the paper. This is staggered because hydrogens are far apart. This is eclipse, so they are only producing minimum distance. Next is Sohos representation. Here they are slightly viewed from above from right. Here the central bond is drawn diagonally. You can see it from a figure, and this is staggered because the hydrogens are far apart, and this is eclipsed. Newman projection, it is very simple method of representation. Here a hydrogen atom is very near to our eye, and they are represented by point or a line, and carbon atom is very far away from our eye. It is represented by circle. There is a 3 atoms or groups that is attached to the carbon atom having the same angle, that is 120 degree. You can see that here 120 degree. This is staggered form and this is eclipsed form. See, the carbon is denoted in circle and the hydrogen that is represented by point of a line. Sometimes they can be represented by point. Here it is represented by line. Then relative stabilities. That is, in eclipsed conformation, hydrogen atoms are close to each other. So that's about 2.29 degree. Whereas in staggered, hydrogen atoms are far apart. So they're having 3.14 degree. So while comparing with staggered, energy is more for eclipse, that because of repulsive attraction force between the CH bonding electrons. So at starting we came across a graph. See, this is the eclipsed and this is the staggered. So energy is more for our eclipsed compared with staggered. And this is the graph, that is relative stability graph of ethine. Okay, that's for today. Thank you.